Can you see my slides?
Yes, everything looks fine. Thank you.
Okay, so I will start. So first, thank you very much for inviting me. And I was asked to talk about open questions in binary neutron star and BH neutron star mergers. I was not asked to talk about important open questions. So I decided to talk about open questions that I think that will not be otherwise discussed in this meeting. So I will try to avoid, I will touch a bit about things that are directly related to the actual simulations of the mergers and the ejecta. But you will see, I will talk about 6 different questions, and they are slightly more high level. Now, all I can talk about is question. I cannot offer answers. So, and I will talk about 5 minutes about each question. So if anyone has any suggestion, any thought, any question for clarification, I ask you to interrupt me in the middle of the talk and not at the end, because it's really different, completely different topics one after the other. Well, not completely, but not directly related topics one after the other. So I think that we can have discussion during the talk and not after the talk. This is my suggestion, if the chair is agreeing. Okay, so what are the questions I'm going to talk about? First, I would like to talk about the massive component of the ejecta that we have seen in GW 170817 and asking where it comes from. And I think there is a bigger problem than just being fast and blue. I will explain why. Then I'm going to highlight a point about the energy budget of the jet in short GRBs, but most of the information is coming from GW 170817, which I think that is usually not well appreciated. I will also talk about analogy to long GRBs, which I think is quite interesting. Then I will switch gear to talk about the fast tail of the ejecta, why it is so difficult or practically impossible to simulate, and why it is so important observationally. After that, I will talk a bit about the recent observations of what seems to be a long GRB with kilonova emission. Then I will talk about a question that is related to part of what we saw in the previous talk, which is where are all the magnetars? Why we do not see the magnetars that I think should have been existing if we understand correctly the observations. And finally, I will talk about something which is completely different, and I will also need to explain for a few slides what is how do I get to this conclusion. But my conclusion is that the gamma ray emission in short GRBs and also in long GRBs shuts off abruptly. It's counterintuitive. I do not expect it naively to happen. And I will ask why. I don't have answers. So let's start. So the first question is on the energy budget of the subrelativistic ejecta. Where does the fast and massive blue component come from? So if you look at GW 170817, one of the more robust results is we need about 2% of a solar mass to be ejected at a velocity of about 0.2 to 0.3 C. We know that because we have early, I mean about half a day, emission of 10 to the 42 ergs per second. We know what is the heating rate from the R process elements roughly. We know what is the velocity just from the photosphere and the curve. And this is rather robust. Now, if we just look at the energy, then the energy in this material is about 10 to the 51 ergs. Now, as far as I know, and maybe during this conference, people will show that I do not know enough. Simulation do not get 10 to the 51 ergs in the ejecta, in any type, in any part of the ejecta, at least not easily and not with the masses that we we saw in GW 1708-17 and with what we expect to be a consistent equation of state. So first is the dynamical ejecta. Now the dynamical ejecta is fast enough. It is probably blue, so lanthanide free, but usually there is not enough mass. So the typical mass in simulations is a few times 10 to the minus 3 solar masses. So the energy is about 10 to the 50 erg in this ejecta, and not enough. If we look at the secular ejecta, this is even more robust. It depends on the mass of the disk, and even if you lose, I don't know, 50% of the mass of the disk, the velocity will be much lower, around 0.1, maybe 0.15 c. The mass will probably be enough, but the energy again is short by at least a factor of a few, probably around an order of magnitude. So I'm not familiar with simulations that are fully consistent with what we observe, even with just the amount of energy, just the amount of the kinetic energy. Now, maybe there are, I don't know. I opened several papers on the topic with all the tables and looked at the total kinetic energy, and except for extreme cases, I didn't see enough. So one possibility is that this energy is coming from an engine. So we know that there is an engine. Something should produce the jet. Maybe this engine is also producing additional, depositing 10 to the 51 ergs into the sub-relativistic ejecta, and thereby at least solving the problem of the energy. Otherwise, I will be happy to hear suggestions. So before I go to my next question, I would be happy if there are any comments on that. Okay.
So the only question or comment for this part?
I have a question for Udi. Can you guys
Okay.
hear me?
Sure, Phil, go ahead.
Udi, just out of curiosity, like these numbers seem to be pushing it just a little bit. Like, so for instance, why do you think it's up to 0.3 C? And why do you think it's up to, well, this is less crazy, it's 0.02 solar masses?
So first of all, the 10 to the 51 you obtain with 0.2 solar masses, 0.02 solar masses and 0.2 C. But the 0.3 is just coming from what we see early time. So you have, first of all, you can measure the radius from the early time spectrum is is almost like a black body, so you can measure the radius for that. And also you need to have a velocity that is large enough, so you will release, so the optical depth will be low enough to release all this energy which is deposited by the radioactive decay. But the 10 to the 51 ergs is really not pushing it, I think.
I mean, I actually happen to agree with you. I think just a little bit of reheating of the ejecta can explain the early time blue light curve. All right. But I'm not sure if you require. I mean, it's a small change. I don't think you require 10 to 51 ergs. Probably 10 to 50 is sufficient, basically, and I think it's close to 0.1 C. But I mean, like, that's just minor details here and there.
Okay.
Okay. There is a one more common question from David.
Hi. Yeah, I just wanted to make a comment that we proposed a possible explanation a couple of years ago with a spiral wave wind. According to our simulations, if the remnant survives long enough, because of hydrodynamic torques of the remnant on the disk, you naturally produce ejecta with the kind of velocities and masses that you need. I'm not sure that this is the right explanation. It's definitely not the only explanation. But if you assume a lifetime of the remnant of 200-300 milliseconds, so extrapolating our simulations in the future, then you do get these numbers of 10 to the 51 ergs and 0.2 to 0.3 C. and 0.22 solar masses.
Thanks.
That's a very good point. Thank you, David. Is there any more comments before we let Udi go on the next topic? All right, Udi.
Yes, there's
Oh
one
no,
more
Wolfgang.
question.
Sorry, I see one more. Wolfgang Castal, is that you?
Yeah. So just a quick comment. I think your idea that there is some injection from the source could also be an explanation. I mean, there are some simulations where you have large magnetic fields and those even unbind matter from the outer layers of the not yet collapsed neutron star remnant. Of course, those simulations are a bit pushing it, but it's not out of the question that this might be possible. So magnetic fields might be indeed another. I just have no idea how fast this ejector should be and about the mass, because one cannot really trust this kind of result yet.
Okay.
Okay, so I will go to my next question, which is a bit related, and also you will see that the conclusion might be the same. So now I would like to talk about the energy budget of the jet and then compare it to long GRBs. So let's look at what we had, or what the nature had in GW170817. So we assume that it seems that the accreted mass and also the ejected mass was roughly a few percent of a solar mass. So the available energy from the accretion is about 10 to the 53 ergs, if we can convert all this energy to an outflow. Now, if we look at the jet, and we have quite a good estimate of the total jet energy because we know the geometry, it was about 10 to the 48, 49, and 10 to the 50 ergs. So if we just take the total energy, how much energy we need to extract from the accretion, it's about 10 to the minus 3 to 10 to the minus 4 m accreted C squared. Now, this is not trivial because usually, if we have an efficient accretion, which is converted to an outflow like a mud state, we get much higher efficiency. If its efficiency is very low, usually the outflow carries less than this amount of energy. So, I think most of the studies which are trying to produce jet are not trying to aim to this level of efficiency of about 10 to the minus 3 to 10 to the minus 4 m accretion C squared. It might have something to do with changing orientation of the magnetic field, and then we have efficient, inefficient in some way. I don't know, but I think that one thing that people that work on jet production need to think about that. Maybe it's also making it easier. I don't know. If I just want such a small fraction of the accretion, it might be easier to do. Now let's look at long GRBs. If we look at long GRBs, then roughly the amount of material which is accreted is of the order of 1 solar mass. Okay, so we have a collapsar, which is a collapse of the core, probably to a black hole. Then we have an accretion on this black hole coming from the regions where the specific angular momentum is such that the material is falling to location where it can accrete efficiently. I would say 1 solar mass is roughly the amount of mass accreted. So we had talked about 10 to the 44-ish erg, which is available in long GRBs. If we look at the jet, and we have different estimates of the jet from radio at late time, about 10 to the 51 ergs are emitted in the jet itself. So again, we have an efficiency of about 10 to the minus 3 out of the available energy in the accretion. Now, long GRBs are not followed by kilonova, but they are followed by supernovae. And the supernovae which are following long GRBs are very energetic, much more energetic than typical ones. And we are talking about energy of between 1 and 5, 10 to the 52 ergs. So altogether, if we look at long GRBs, we have a 10 to the 54 ergs accreted. We have 10 to the minus 2 out of that in energy, which is going in a subrelativistic ejecta, and we have 10 to the minus 3 times that energy, which is going in the jet. And if we look at short GRBs, we have about 0.1 solar masses accreted, 10 to the minus 2, which is going in the Newtonian wide outflow, and 10 to the minus 4 to 10 to the minus 3 ergs, which are going in the relativistic collimated outflow. It doesn't say that short GRBs and long GRBs have exactly the same mechanism and everything. But for example, the long GRBs do not have dynamical ejecta. Okay, there is no collision between two things in the center of long GRBs. Yet we have this analogy, which might be a coincidence. Maybe only the jet is related, maybe not. I don't know, but it's tantalizing. Maybe the energy in the ejecta here in the short GRBs is coming again from something which is happening near the central engine. Maybe the same energy is also what driving the supernova. I don't know. The fact that in both long and short GRBs we have the same efficiency for the jet, I think it's also an interesting, possibly coincidence, maybe not. Again, questions, no answers. If anyone want to comment on that, I will be happy.
Hi, Udi. Can I ask a question?
Yeah, of course.
So short GRB case or GW1717, we know only one event. On the other hand, long GRBs, it's the energy in a jet is widely distributed. So is it not fair to say the typical parameters are like 10 to the 52, 51 now, or there are maybe more weaker long GRBs that change this?
So in long GRBs, I think that we have quite a few observations. The 10 to the 52 ergs for the supernovae, in all cases that we observed, we have, I don't know, half a dozen maybe. And the 10 to the 51 ergs, there is a range, of course. But I think it's a typical number. It's a typical number for long GRBs. For short GRBs, everything is typical for one event. By the way, we know that in some cases, we can use upper limits on kilonova emission from some short GRBs to show that there are mergers which probably produce less than 10 to the 51 ergs in the ejecta. It's almost certain. So maybe if we have more observations and everything that I'm writing here will become inaccurate in the short GRB part. But yes, based on this single event, this is what the best I can say.
Yeah, thanks.
Yeah, but you're correct. I should be less conclusive. Any more comments? Oh. So my third question is what are the properties of the ejecta fast states? So in many simulations, there were also some analytic expectations. It seems that there is some minute fraction of mass, and I will talk in a second about what I mean when I say minute, which is moving fast. Fast is faster than 0.6 C. There are also suggestions that there is material extending also to high Lorentz factor of 2, 5, 10. Sky is the limit. And why do we care? And I would argue that we care because of that this fast tail may have a very strong implication for the observation, and in our case for the gamma ray emission that we saw in GW170817, and we might see also in the future. Now, to explain why we expect to have, why the fast tail is important and what will be the implication for the observations, I will show a short simulation done by Or Gottlieb. Was a student of mine, now he's a postdoc in Northwestern. So what you see here is the following. You see the ejecta. In the ejecta, we take two parts of the ejecta. This central part is what we call the massive ejecta, is velocity of 0.1, 0.2 C, mass of about a few percent of a solar mass. And then here we have the fast ejector, fast and fast tail. The mass in the fast tail, I don't remember, but it's 10 to the minus 5, 10 to the minus 6 solar masses, and it extends out to velocities of about 0.7 c. Okay? And now what you will see here is a simulation of a three-dimensional jet, which is injected into the ejector, and now it's going through the massive part. As soon as it's going to the diluted part of the ejector, it started to expand, and it's driving a cocoon, which is breaking out at this point. Now, at the time that it's breaking out, it's producing a flash of gamma rays, which fit quite nicely what we saw in GW170817. And later on, it continued to expand. Here you see the different components. So you can see the jet in the center. You can see the cocoon. The cocoon has two parts, internal and external. I'm not going to talk about that. And you see the ejector. And the jet, of course, is supposed to produce the GRB. The ejector is supposed to produce the kilonova. And the cocoon itself, during the breakout and also during the first hour or so, possibly even several hours, is supposed to produce its first gamma rays and later emission at lower frequencies. Now, what is the amount of mass that we care about? Now, if we estimate what is the region where the optical depth is of order unity, this is a region which is producing the shock breakout. So if the breakout takes place at a radius of 10 to the 12 centimeter, then the mass is about a few times 10 to the minus 8 solar masses. So this is enough. It's enough if there are 10 to the minus 8, maybe 10 to the minus 7 solar masses, which are running ahead of the main ejector, which is produced presumably during the dynamical ejector, which is moving at a velocity of 0.7, 0.8 c, to make a tremendous effect on the shock breakout and the gamma ray emission that they produce. I don't think that any simulation can get down to this amount of mass, but this is the level of precision that we need to predict what would the shock breakout look like. Now, if we take this amount of mass moving at this velocity and we measure what will be the amount of energy in the breakout, then for the same radius of 10 to the 12 centimeter, we'll get the amount of energy that we saw in GW170817. And these are all these gammas are the Lorentz factor of the shock in the rest frame and the Lorentz factor of the shock in the upstream frame, which in this case is the fast tail. The details are not very important. Well, they are, but not for our sake. And the temperature that we expect, so what will be the energy of the photon, that was supposed to be about 50 keV for a mildly relativistic shock. Now, nice thing that we have in this model is that there is a closure relation. So there are more observables than actual physical parameters which determines the emission from the shock breakout. You can see that for an energy of about 10 to the field 46 ergs, and if most of the emission is coming around 100 keV, we expect the duration of this breakout to be about 1 second, which is roughly what we saw in GW170817. Now, this breakout must take place. It's unavoidable. You have some subrelativistic outflow, which starting moving as soon as the two neutron stars collide. You have jet which is coming later. This jet to produce the short GRB must go through this ejector. The shock must break out. Gamma rays must be produced. It can be fainter. It can be brighter, depending on the radius. If the radius was lower by if the breakout took place at 10 to the 10 centimeters, the gamma rays would be much fainter. If it would be at a larger radius, it would be much larger. But it must be there. It can possibly be observable, and at least my view is that this was probably the gamma rays that we observed in W17 or 817, and there is a good chance that this type of gamma rays will be observed also in future events. More chance in observing actually the off-axis emission from the jet. The short GRB itself after deboosted to an off-axis observer. So this is a question that I ask the community. What can you say about the velocity of outflow of a mountain of about 10 to the minus 7, 10 to the minus n solar masses? And again, I don't have an answer. Any question or comments?
Both can.
Yeah, what I'm missing in this chain of arguments is the delay of the jet formation. So wouldn't that crucially impact when the breakout happens and at what radius? So isn't that an unknown factor here?
Yeah. So when I say radius, it's basically a combination of the velocity of the tail and the delay. So the answer, yes, it depends on the delay. For example, in the case of GW17 or 817, we needed a delay of a few fraction of a second, so 0.2, 0.3 seconds to get the correct radius and something which is comparable to what we observe. But still, there are more observables than 3 parameters. So if this was a shock breakup, I can tell you what was the delay. If it was something else, I don't know. But yes, the delay is affecting the radius, and the radius is affecting the brightness and the duration and everything else. Yes, it does.
So this was specific to 17 or at 17. It's not supposed to be a more general.
No, this is here. It's completely general if you plug in the specific parameters. 10 to the 12 centimeter is specific to what we need to explain GW17 or 817.
Yeah, that's what I meant. Thank you.
All correct for any type of shock breakup. Okay. But yes, taking these parameters is what fits the observation of GW17 or 817. But the question of what is the fast tail is important for everything. So even if we didn't see in GW17 or 817 shock breakout, there is a good chance that we will see it in future events with reasonable parameters and reasonable jets and reasonable delays and reasonable everything. Not guaranteed, but possible. Julia?
More comments or questions concerning this point? This is very teasing. Julian?
Yeah. You mentioned that merger simulations show something like 10 to the minus 5, 10 to the minus 6 solar masses at speeds above 0.6 C. And how good are the simulations at resolving such a small amount of mass?
You should ask David about that. I think that the answer is not very well, but everybody agrees that. So all simulations, all different simulations give the same. But let David answer that. He knows better than me.
Oh, okay. Yeah, I just wanted to comment that it's very uncertain, but recently there has been a very interesting work by Rodrigo Fernandez where they did a very careful systematic study of fast eject as a function of resolution. These were Newtonian simulations, but they could afford incredible resolutions. And they claim that current simulations are not off by more than an order of magnitude in the amount of ejecta mass. So the error they estimate are not actually that large. But I also wanted to ask something else. Apart from the total amount of mass, what do you need to know in order to predict the signal of the breakout? Do you need to know something about the stratification of this outflow, or essentially you're only sensitive to the total column density?
So what I need is a mass, the delay, and the velocity of the ejecta. It depends, so I need to know the certification if I want to be better than doing that. I need to know. It's better to know that, but even without it, I can give a rough estimate. This is the answer. Because the reason, I will also explain the reason. The reason is that the emission depends on a very small amount of mass, which is where the optical depth is of order unity. So if there is maximal mass, then I don't care about almost anything. If there is a maximal velocity, if I know that there is a maximal velocity and after this maximal velocity there is no more mass, then I don't care much about the specification because the emission will be from the edge of this outflow. If there is the outflow extended to very high velocities, then the breakout can take place not because the shock reached the edge of the ejecta, but because it just reached the point where the optical depth to infinity is low enough. And then I need to know where is this point to know what will be the emission. Okay?
Okay, this is clear. Thank you.
Okay. Yeah. So, yes, Wolfgang?
Yeah, it's just a comment on your actual question. So speaking only for my simulations, I wouldn't trust such low masses at all, like really not at all. Of course, this all depends critically on all kinds of factors. For example, what kind of artificial atmosphere? Is it becoming less or is it constant? How big is it? And what kind of numerical methods? I think for these incredible small effects on the scale of the whole system, one really has to be extremely careful. And I don't know if a comparison to some Newtonian simulation, which might all kinds of things differently, is
No, but I would just say one thing. In the simulations, usually what you see is about 10 to the minus 5 solar masses, 10 to the minus 4 solar masses. Do you trust this amount of mass?
So I think you were specifically asking about the fast ejectors.
Yeah, something which is moving faster than 0.60, 0.6, 0.7. Yeah.
Yeah, and I mean, if it's something like 10 to the minus 5 solar masses, I wouldn't trust it just because it comes out of the simulation. This would have to be a really careful study how this propagates. And so again, speaking for my simulations, people might have different codes which are more well investigated in that respect, but just to give you one data point.
Okay.
Right. In our simulations, the amount of artificial atmosphere is about few times 10 to the minus 7 solar mass. So we think the ejecta mass more than 10 to the minus 6 solar mass probably okay, but I don't know what other people think. Maybe David may have comment.
Yeah, for me, it's convincing the fact that ejecta is much more in mass than the atmosphere mass, and also there are different results by different groups using completely different methods that seem to agree on these numbers. Then whether it's 10 to minus 5, 10 to minus 6, or 10 to minus 4, I would not dare to say. But there are simulations unpublished, but I think maybe Stefan Roscoe could talk about them in the next days that he presented at some conference where using the new SPH with BSSN, they also find similar values. There are simulations by Kento Tokezaka, my simulations, and we find kind of comparable numbers. And again, these simulations by Rodrigo Fernandez really achieve convergence. So you can see the error going to 0 at a given rate as a function of resolution. So that's very convincing that at that point you have the right numbers.
Can I just comment on that? It's Stefan here. So, and also to Wolfgang says that we have these, well, BSSN, SPH calculations which have no atmosphere problem whatsoever. Of course, we don't have a fantastic resolution there. It's, well, not too many particles, but they very nicely extend to these velocities, and well, we don't have any atmosphere problem whatsoever. And the numbers are relatively similar to what Davide and also I think Daniel Siegel recently has been seeing.
Okay.
Okay.
So I will go on to the next question, but this one I will go fast, and because I see that I'm a bit short in time, will not comment on that one, okay? Because the others are more interesting. So my question here is very simple. For a long time, everybody tried to show how we can get a short GRB through merger, namely a jet which is an engine which is working with a typical time scale of about 1 second. There were hints already from 2006, but now it seems to be clearer that there are long GRBs in the sense that the engine is working for longer, much longer than a second, longer than for tens of seconds, certainly. If we understand something about the origins of the prompt emission, then it must be a long-lived engine. And I must say that, at least for myself, the suggestion that what we see in the afterglow is kilonova is quite convincing, much more convincing than anything else that I saw so far from GRBs. So I really don't know. This is, by the way, the light curve of this GRB that was published recently. You can see it highly variable for about 10 seconds. It continued to be variable for another 20 seconds. Which is indicating about an active engine. So now we have another thing that we need to know how to do. And nature knows, we do not yet. And I don't know, I don't have a good answer. If I would have to guess, it would have something to do possibly with fallback of material back, with fallback of large amount of material to be accreted at late time, but it's just a guess. So let's go to the next question. My next question is where are all the magnetars? Maybe I did hear something wrong. So please correct me if I did something wrong in my arguments. In the following arguments, something that I thought about last week when I tried to think about questions for open questions. So I thought, what would happen if the binary pulsar in our galaxy will merge, and it will merge. 100 million years from now, it will merge, but there are many like this in the universe which are merging right now. So if we look at the rate, the predicted rate of mergers based on galactic binary neutron stars, then the rate depends on what is the lifetime until merger and what is the distance to which we can detect them. And this is converted to a rate, and the dominant factor, so the most, if we take the galactic binary neutron stars, the ones which are predicting to produce the highest rate are systems like the binary pulsar. Now, the binary pulsar, as I said, will merge in about 100 million years. The total mass is about 2.5, 2.6 solar masses for the two companions when they are far away, of course. Now, after the merger, I need to reduce the gravitational mass. I get about 10 to the 35 solar masses, and this is also without ejecting. If I'm ejecting 0.1 solar masses, I will have even less. And this put me safely below the line that was shown in the previous talk about for the supermassive neutron star. So I expect, and please, this is the part which I'm not sure that I'm correct, I expect the binary pulsar to produce a supermassive neutron star. So it's massive enough to collapse, but it is stable as a rigid rotating object. Now, we expect if we have a rigid rotating central object which was just formed due to the merger of two neutron stars, we know that magnetic field is very strong. We expect dynamo to work, so we expect to have a magnetar. If we have a rapidly rotating magnetar, and this magnetar is not going to collapse until it slows down. So it needs to slow down. It's slowing down by injecting energy into the ejector. The amount of energy is a few times 10 to the 52, almost 10 to the 53 Hertz. So we expect to have an ejector with more than 10 to the 52 Hertz. Now, if I go back here and I say that the rate is high, then, and I know that the rate for neutron star merger is about a few hundreds to 1,000 per gigaparsec per year. Let's take about 10% of these to come from systems like the binary pulsar. We expect to have very strong radio resonance, which are coming from this energetic event, and we don't see them. We just don't see them. So there are now surveys in the radio we can put a limit on how many objects can be there. What is the rate of explosion? We say 10 to the 52 erg. This is something that where the velocity is larger than about a Lorentz factor of about 2 or something like that. So we can ask this question, and this rate is lower, much lower than the rate of binary neutron star mergers. By the way, there is a similar questions for magnetars from core collapse supernova, but something here in this chain of arguments is wrong. Obviously, it might be this one. Maybe the rate is low. Well, we know that there are such systems. We see one. We actually see two in our galaxy, but maybe the rate is much lower than what we predicted based on this event. Another possibility, okay, maybe no magnetar is formed. We don't know. We think that magnetar, that these are optimal conditions for generating a magnetar. Maybe it's not. Maybe magnetars are produced differently than the way we think. And the last possibility is that we do something wrong with observation or the modeling of the emission, of the radio emission. Maybe the radio emission is much fainter than we thought. But one or more of these different arguments must be wrong. And I don't know what it is. If anyone can help me, I will appreciate it very much.
Well, that's very interesting. Okay, so we have a question.
I have a question. I mean, how did you get the energy? I mean, you have to assume the rotation speed. I mean, so.
I assume that the rotation is a millisecond rotation. That's it.
Why?
I know it is the angular momentum of the system.
Yeah, but I don't know exactly what
the
is
angular momentum just went to the central object, no? It's emerging neutron star.
Right. But you know,
I know what is the angular momentum of the system. Two neutron stars which are just merging.
Well, in long GRBs, it's at least in core collapse, it's unclear what's the rotation. I mean,
I know.
The 3 milliseconds that was advertised.
I know. In long GRB, the question there are different line of arguments, and it's easier to be wrong.
Well, so here could relate it to the question how exactly I mean, if you believe that the dynamo amplify the field in milliseconds, and you get actually an ordered field like a dipole field, then yes. I mean, it's not enough to amplify the field. You need 10 to 15 Gauss dipole component. Right?
Yeah. I know. You need to produce a magnetar. But magnetars are produced. We see them. And the main suggestion is that what you need is fast rotation and a lot of energy that goes into the magnetic field, and we have both. So maybe
but maybe the field initially is buried, for example, or something of that sort.
But you have a long time, so you have 1 year to get rid of this energy. If you do it within about not 1 year, but let's say 1 month. If you do it within a month, no, a year. If you do it within a year, you will see it in the radio. So you need to prevent the central object to lose its energy for more than a year.
No, I'm saying suppose that the dipole component form, you form strong field initially, but the dipole component forms after only when the rotation speed is 10 milliseconds. For some reason. I don't think we understand this process, but yeah.
No, okay, yeah, maybe this is the weak link, maybe.
Mm-hmm. So Wolfgang, you had your hand raised.
Yeah, I hope I'm not hogging the discussion here with all the raised hands. So I think the amount of energy in the rotation would be enough. I don't buy the angular momentum argument directly because gravitational wave emission during merger is significant in this respect. But that's not my main point, that you still have enough. But I think also that one should not confuse a large amplitude magnetic field with something like an isolated magnetar field where that is even simplified to be a dipole. I mean, it can be very unordered. It can be, even if it seems like it's, let's say, strong ordered dipole, the field lines can go in very opposite directions, depending how this is created. So the use of like the dipole energy emission of a rotating misaligned dipole, I would not bet any money on this. And I would expect that an unordered field makes the energy emission slower. So that might be a weak link.
1 year is
Yeah,
a long
that's
time. Naively, you would expect to emit the energy within seconds. If you have a dipole and this amount of and 10 to the 15 or 10 to the 16 Gauss, you will emit it within seconds.
You mean with a dipole of this magnitude?
Yes.
Yeah, I mean that's the argument, but I think we don't really have a good model for the morphology of the magnetic field of a merged remnant, and so this is a bit difficult. This question, how much and how fast this energy is released. And I should also note it's not just rotation. So the supramassive neutron star that it forms is also differentially rotating normally. So you can actually release more energy than you would just based on angular momentum loss, as another remark.
So I agree, there are many things that we don't know here, but I think that the naive picture would be as I plotted here. And something here is wrong. It might be the configuration of the magnetic field or the strength of the magnetic field or all the observations, yes. But maybe this is indeed the fast rotating magnet, or maybe this is the weakest point. It's possible. Do I have some time for another question?
Not really. There is a break, but is it fast?
I can make it very fast.
Okay, go ahead.
So my point is the following. In almost any engine that you will think about, there will be some characteristic time for the engine. For example, if you have accretion, you will have some characteristic time over which the accretion takes place. And then at longer time, it's supposed to decay. Is it exponential? Is it very extreme? More likely like a power law. Also, if the energy is deposited by rotation of, say, a magnetar, it will decay as a power law. So we would expect that if we have an engine for the GRB, for the jet, that this engine should have some typical time after which it's becoming weaker, but with a comparable time to the working time of the engine. Okay. Now, if this is correct, then we would expect that this decay would be seen in the light curve, in the gamma ray light curve. So the gamma ray light curve is composed of the energy in the jet and the efficiency which is producing the gamma rays. And assuming that the efficiency is not changing without any reason, we would expect that the engine is becoming weaker with time. And then if we look at different pulses, we would expect to have brighter pulses at first and then weaker pulses as we go on and on. Okay? Now, in single GRB, we cannot see it because there is a lot of variability, and this variability can come from the dynamical time scale of the engine. But what I did, and this is something that I did, I don't have time to explain exactly how. It's not very complicated. I thought it was done before, but I couldn't find any paper that did it, so I did it myself. What you see here is the average light curve of 36 short GRBs. So I took 36 short GRBs, I normalized them all, I summed them together. And what you see here is how much energy is emitted as a function of time compared to the duration of the burst. And one of the things that you see here is that you have roughly a constant emission. It's rising, okay, for about 10% of the duration of the burst. It's constant for 80%, and then it goes down in the last 10% of time, of duration. So if at least the gamma rays themselves shut off almost immediately on a duration which is much, much shorter than the duration of the emission of the burst. It can be that the engine shut off somehow. It may also be that the efficiency shut off for some reason. I don't know. By the way, you have the same effect in long GRBs. And again, I don't know why. Naively, I would expect to have a gradual shut off of the gamma ray emission. I would expect to see it in the light curve. I don't. So maybe there is something wrong with my expectation to see it in the light curve. Maybe it's the efficiency, maybe it's the engine. But again, it's a puzzle that I don't have the answer to. And that's it. Thank you very much. It was fast enough.
Wonderful. Thank you for teasing so much